For many decades, physicists thought that black holes are completely black, not even allowing light to escape. After all, given their extreme space-time curvature, black holes relentlessly trap everything within their grasp. A standard joke was, what do you say to a black hole to make it feel self-conscious? Oh, I think I saw a little flash of light there. General relativity is an amazingly successful theory, so why should we doubt that black holes don't shine? Well, the conclusion that black holes are truly black is a purely classical view, that is, based on classical Einsteinian relativity. Might the situation be different if quantum mechanics is taken into account? Now, the basic idea behind quantum mechanics, or quantum physics, is that particles don't have definite properties such as position, speed, and energy until one actually measures them. Even then, the specific outcomes of the measurements are probabilistic, not deterministic. Also, one can't determine all the properties precisely, certainly not simultaneously. There are uncertainties involved. Now, this sounds weird, but in fact, quantum mechanics is an amazingly successful theory. It correctly describes the inner workings of atoms and molecules. We've never found any violation, when we apply quantum mechanics to its domain of applicability. Much of our modern technology, including computers, digital cameras, lasers, and other devices, is governed by quantum physics. Well, what if one applies quantum physics to black holes? All right, well, the basic problem is the following. You can't ignore general relativity when you're talking about black holes. So if you want to apply quantum physics as well, you've got to apply both theories. But when general relativity and quantum physics are used to describe a large amount of mass in a small volume, such as the singularity inside a black hole, there is violent conflict. These two theories are completely incompatible with each other and give nonsensical answers. Indeed, they are utterly at war. Even the nature of empty space, it turns out, cannot be understood with the two theories together, at least at this stage of our understanding. So the holy grail of modern theoretical physics is to unify its two great modern pillars, quantum mechanics, which deals with the very small, and general relativity, which deals with the very large. Each works amazingly well in its domain. Quantum mechanics on the very small scales with light particles, general relativity on large scales with massive objects. With the quantum theory of gravity, however, we would presumably be able to understand the singularity inside a black hole, where a large amount of matter is concentrated into a very small volume. Though we don't yet have a fully self-consistent, unified theory of quantum gravity, Stephen Hawking of Cambridge University came up with an interesting result believed to be generic to such theories, regardless of the specifics. And that result is black holes can evaporate due to the presence of what's called quantum fluctuations. Now here's the argument. It gets pretty complex along the way, but I'd like to give you the gist of the idea. Don't worry about the details, okay? Just like in the previous couple of lectures on falling into a black hole and all these weird geometries, don't worry about the details, just get the general idea. My account will be in the roughly historically correct order so that you'll see how these notions developed with time. Now, black holes are very simple. As seen from the outside, they can be described entirely by their mass, their spin, more correctly known as angular momentum, and their electric charge, regardless of what kind of material went into a black hole. And we don't even expect real black holes to be charged. Since they would rapidly attract an equal number of opposite charges, they would neutralize themselves. Electric forces are really strong. John Wheeler understood this aspect of black holes, their simplicity. In fact, as with the terms black hole and wormhole, he had a catchy way of stating it. A black hole has no hair, no details, only mass, only angular momentum, spin, and charge. So here you have a black hole with hair. Nope, doesn't exist, folks, doesn't exist. Throw in books, dinosaurs, buildings, stars, planets, giraffes, bricks, computers, TVs. It doesn't matter what you threw in. They're all the same as long as the mass, the total spin, and the electric charge are the same. That's the only thing you can know about the black hole. Note that this applies to a black hole that has had time to reach equilibrium. When, for example, black holes initially merge, gravitational waves are emitted, and it looks really complex. You know, they're all rumbling around. But after a rather short time, compared with the merging process itself, it stabilizes. The gravitational waves themselves carry away any remaining details about the black hole. So look at this merging pair of black holes. The contours there represent gravitational waves being emitted during the merging process. By the way, how do two black holes greet each other? With a gravitational wave. Anyway, look at those things there. I know, corny jokes. My students have to put up with me every day. Now you do too. So look at that complexity. The gravitational waves are carrying away all the details, and after they've merged to form a single black hole, additional details are carried away by the gravitational waves until the black hole is utter simplicity, mass, electric charge, and spin. All right, well, let me now talk about entropy. Entropy is a measure of the amount of disorder. It turns out to be proportional to the natural logarithm of the number of macroscopically similar states. You can take the logarithm on your little calculator. Now, a black hole having no hair seems to have very little, if any, entropy. Let me give you an example. Suppose I have 10 coins, all tails. The only way to do it is one way. They're all tails. The logarithm of 1 is 0. You can try that on your calculator if you don't believe me. 0 entropy. Now suppose I have one head, 9 tails. There's 10 ways to do that. Each of the 10 coins could be the head. So there's some entropy. You don't know which coin is heads unless you look carefully. With 2 heads, there are 45 ways to do it. That's more entropy. With 5 heads and 5 tails, there are 252 ways to do it. Even more entropy, okay? Now, the second law of thermodynamics is that in any natural process, the entropy of a closed system, by closed I mean nothing escapes, always increases, or at best stays constant. It almost never decreases. If it does decrease, it's a huge statistical fluke, very unlikely to happen again. It could happen. Nothing in the laws of physics, strictly speaking, prevents it, forbids it, but it will almost never happen. For example, all the air molecules in this room could suddenly go rushing off into the corner, and I would asphyxiate. That could happen. But in fact, it's not going to happen. You'd need a universe far, far older than ours for it to likely have happened even once. It's statistically highly, highly unlikely. Now, the second law of thermodynamics is often misunderstood. After all, if some water molecules freeze to form a snowflake, which is highly ordered, the entropy appears to have decreased. But remember, this is not a closed system. To freeze the water into the snowflake, you had to carry away energy. Energy was radiated as photons, thus increasing the overall entropy of the universe. All right? The entropy of the snowflake decreased, but the entropy of the rest of the universe increased, and the total system entropy increased. Well, thermodynamics is the study of the relationship between heat, work, and other forms of energy. There are 4 laws. The second law is the most important by far. It plays a huge role in governing the physical universe. Again, that second law, in any closed system, the entropy can only increase or at best remain the same. Well, what happens to the entropy when you throw stuff into a black hole? You throw a bunch of material into a black hole, it's hidden from view. It seems like there has been a loss of entropy in the observable universe. The innards of the black hole are not observable. So the stuff that's gone in has carried its entropy with it, and it looks like the second law has been violated. The observable universe now has less entropy. Well, in 1972, physicist Jacob Bekenstein was deeply troubled by this apparent violation of the second law of thermodynamics. He said, well, maybe the black hole itself really does have entropy, and it is associated with the surface area of its event horizon. That might be the case. On the other hand, if the event horizon is smooth, remember, a black hole has no hair, how can this be then? You know, how does it have a whole bunch of entropy? Well, the smoothness, in fact, provides the clue. Let's look at a bunch of dots on a page. Suppose we have 2 concentric circles, with the middle one colored black and the other one white. That is, the annulus is white. One such combination exists. There's a strong pattern, sharp edges, low entropy. The inner circle is black, the outer annulus is white. There's only one way to do that. But if we randomly distribute those same black and white dots, we get a uniform gray. There are lots of microscopic combinations which would give the same overall looking result. Lots of microscopic combinations means a high entropy. So macroscopically uniform, bald appearances in fact are associated with high entropy. Through a magnifying glass, we would see lots of randomly scattered black dots. And any particular configuration would be different. This one looks different from that one, and this one, this one, this one. So if you looked carefully, there'd be lots of configurations, each of them different. But overall, they look the same. High entropy, kind of like the molecules in this room. So a smooth distribution can contain a lot of entropy. A black hole with no hair has a smooth, seemingly featureless event horizon. Perhaps the entropy is hidden there. Well, Bekenstein went on to calculate that one can indeed think of the entropy being hidden on the event horizon in tiny little patches of area. And as you throw more matter into the black hole, the entropy increases. The horizon size also increases because the event horizon radius is proportional to the mass of the black hole. Well, if matter or energy, photons, are added to a black hole, the mass increases. Classically, nothing can come out of a black hole. The radius increases. The Schwarzschild radius is 2 times Newton's constant g times the mass divided by the speed of light squared. The event horizon is spherical. The surface area of a sphere is given by 4 pi r, the radius squared. So the surface area is proportional to the square of the mass. If the mass increases, the surface area increases as well. Since the mass can never decrease, the surface area, similarly, can never decrease. So, if the surface area of a black hole can only increase or at best remain the same if nothing is being thrown in, then it kind of sounds like the second law of thermodynamics. If in any natural process the surface area of the event horizon of a black hole always increases or at best remains the same, and if there's entropy associated with the horizon, then the entropy is only increasing as you throw material in, and this is just like the second law of thermodynamics. The mass is increasing, the surface area is increasing, the entropy is increasing. In the second law of thermodynamics, the entropy always increases, or at best remains the same. So the second law of black hole dynamics, that the surface area can only increase or remain the same, and the associated entropy perhaps can only increase or remain the same, sounds a lot like the second law of thermodynamics. Now there's 0th, 1st, and 3rd laws of thermodynamics and of black hole dynamics that again have similar wording. They sound similar. Black hole dynamics and thermodynamics actually sound similar. So Bekenstein made a bold suggestion. With the analogy with thermodynamics, he made the suggestion that in fact a black hole is physically a thermal body. By a thermal body, I mean a body that has little atoms and things jiggling around, doing that kind of a thing, all right? That is having a temperature. Temperature is a measure of how much things jiggle around. Now, indeed, a black hole even resembles a perfect black body, a perfect absorber. A perfect black body is one where the incident radiation can only be absorbed. It cannot be reflected. It cannot be transmitted through the body. It can only be absorbed. So a truly black body only absorbs radiation. Well, black holes only absorb radiation and matter as well. If black holes behave like thermal bodies, like black bodies in that respect, maybe they behave like black bodies in other respects as well. In particular, maybe they have a non-zero temperature associated with them, in a sense as though they were all jiggling around, like the molecules in my body. After all, normal black bodies absorb radiation and heat up to a non-zero temperature in the process. But if you carry this analogy further, it means that a black hole should radiate. Since black bodies of non-zero temperature radiate or shine, they emit photons of light due to the jiggly motions of the charged particles and the atoms within them. But this leads to a paradox. Classically, a black hole can't radiate. Matter and energy can only go into a black hole. So Bekenstein said, oh man, this is bad. He didn't pursue the idea any further. He felt that this is where the analogy between black holes and normal black bodies fails. The analogy between black hole dynamics and thermodynamics, he reasoned, can only go so far. And he stopped thinking about this. But Stephen Hawking decided to pursue it further. A few words about Stephen Hawking. He, of course, is a very famous physicist at Cambridge University. He was a bored graduate student at Oxford when he contracted Lou Gehrig's disease when he was 21 years old. This is more formally known as motor neuron disease or amyotrophic lateral sclerosis. It's hard to say, or just ALS. In fact, he was expected to live for just a few more years after he was diagnosed. But he outlived the predictions by over 4 decades, turns out. He's now 67 years old. Back to when he was 21. Suddenly, he found a purpose to his life. He was no longer bored. He decided to study physics very deeply, and he came to some truly amazing conclusions. Now, he realized that the conclusion that nothing can come out of a black hole might not hold if you include quantum physics. So he considered the quantum mechanical creation and destruction of particles near the event horizon of a black hole. And in 1975, he published an article suggesting that as a result of these quantum fluctuations, black holes can actually evaporate. They can lose mass and eventually disappear. Oh. He describes some of his conclusions in his popular level book, published in 1988, called A Brief History of Time. Now, in this book, he has only one equation, E equals mc squared, of course. Apparently, his publishers told him that sales would drop to 1/2 for every equation included in the book. I hope you don't mind that I've included some equations here in this course because they add flavor to the whole study of black holes. Well, it's an interesting book, A Brief History of Time, but it's a tough read. It's conceptually very, very heavy. I like to think that it might be the most purchased but least read through to completion book in existence. It's a great coffee table piece. People like to display it in their homes, regardless of whether they really understand it. Then visitors say, oh, you've got Hawking's book. You must be really, really smart, Well, subsequently, Hawking published a couple of other books that explain the concept somewhat more clearly and are more up to date. He has A Briefer History of Time. On the other hand, it's so brief that he covers a lot of ground in very few words, so it's really tough to understand thoroughly. And he has another book called The Universe in a Nutshell. I suggest that you read them if you're interested in some of his thoughts. Hawking can't write equations. Everything is in his head. He's completely immobilized. He clearly has an amazing brain trapped inside an immobile, largely non-functional body. He has become truly an icon, perhaps the most recognized scientist alive today. He's even appeared on The Simpsons and Star Trek and elsewhere as well. That's sort of like the epitome of fame, is when you appear on shows like that. Well, how does this evaporation occur? Here's the basic idea. It's based on Heisenberg's uncertainty principle. Werner Heisenberg was one of the giants of early 20th century quantum physics. Well, one of the most fundamental principles of quantum physics is that if you make a measurement of a real system and you try to measure its energy and its time, the time at which you made the measurement at the same time, there are uncertainties in both the measured energy and in the time at which you made the measurement. And in fact, the product of the uncertainties, denoted here by delta E and delta T multiplied together, is always greater than or approximately equal to Planck's constant, the fundamental constant of quantum physics, divided by 2 pi. Now, a similar relation holds for the product of the uncertainties in position, x, and momentum, p. Momentum is mass times velocity. Delta x, delta p is at least as big as Planck's constant divided by 2 pi. I have a t-shirt that says, Heisenberg says delta x, delta p is greater than h bar. H bar is just h over 2 pi. The equation knows best. You can get these shirts from a company called Purely Academic. It's really wonderful. Well, if delta x, delta p is greater than or approximately equal to Planck's constant divided by 2 pi, This means that you can know the position of an object really well, small uncertainty, small delta x, but in that case you really don't know the momentum or the speed. It would have a large uncertainty because the product of the uncertainties has to be bigger than roughly Planck's constant. Conversely, if you know the momentum, then you don't really know the position very well. Okay? Similarly, if you know the energy precisely, then you can't know when you made the measurement. And if you know exactly when you made the measurement, then you can't get a very accurate measurement of the actual energy. So there's this joke. Heisenberg was driving a car, and an officer of the law, stopped him because he was breaking the speed limit by a lot. And the police officer said, "Do you know how fast you were going?" To which Heisenberg replied, "No, sir, but I know where I am." He knew where he was, but he didn't know how fast he was moving. Okay, well, that uncertainty principle applies to real measurements of real particles. Let's take, in a sense, the inverse of it. Suppose we say that delta E delta t is smaller than h over 2 pi. This applies to what we call virtual particles of energy, having energy delta E, which appears spontaneously for a short time delta t. And if the product of the amount of energy that appeared out of nowhere and the amount of time for which it appeared is smaller than Planck's constant, then in a sense it's not a real object. Okay, you haven't made any real measurement of it. It's a virtual object. This may be a temporary quantum violation of the classical law of conservation of energy. Conservation of energy is just a classical law. Lots of other things are violated in quantum physics, so why not that? And even this might not be a violation. Some physicists think of these virtual particles as coming into existence because they borrow energy from the vacuum and in a sense leave negative holes. So these quantum fluctuations occur all the time. They consist of virtual pairs of particles and antiparticles, matter and antimatter, where antimatter is just the opposite of matter. The positron, for example, is the antiparticle of the electron. When they meet together, they produce photons. Didn't even really matter which type of particle we call matter and which type we call antimatter. We could have called the positron matter and the electron antimatter. It doesn't really matter which one you call matter if you get what I mean, right? So anyway, but here you have all these things forming, living for a short time, and then annihilating. These are quantum fluctuations. Electron, positron, proton, antiproton, neutrino, antineutrino, quark, antiquark. This can even happen with photons. Now these quantum fluctuations exist. They affect the measured energy levels of atoms, like the hydrogen atom. Their presence is inferred in many physical situations. Indeed, their presence is a central aspect of what's called quantum electrodynamics, which describes interactions between matter and light, and which was developed by Richard Feynman and a number of other physicists some decades ago. They won the Nobel Prize for this work because it's been confirmed. Now, near a black hole, quantum fluctuations can occur. And most of the time, these virtual pairs of particles are formed outside the black hole, and they just annihilate each other outside. Or they form inside the black hole, and they annihilate each other inside. Or they form outside the black hole, and then both of them go in. This diagram shows these various possibilities. But notice that there's one possibility that I haven't mentioned yet. It could be that a pair forms just outside the horizon, and then one member of the pair goes into the black hole, and the other member stays outside, and perhaps even can escape to infinity. That's the idea of black hole evaporation. Occasionally, one of the two particles, doesn't matter if it's the particle or the antiparticle, might cross the event horizon, letting the other one escape. The other one just goes off to infinity. This happens most easily when the curvature of the black hole is over a very small scale. The smaller the black hole, the easier it is for these particle-antiparticle pairs to form and have one of them go into the black hole and the other one escape. Because the black hole is small, there's a vast sky out there into which the other one can escape. And so it's simply easier for the little black holes. The other way to think about it is that little black holes have bigger tidal forces than big black holes. So once the particle-antiparticle pair forms, the tidal forces tend to pull in one member and allow the other member to escape to infinity, as shown in the diagram. Now, the one that crosses the event horizon goes in with negative energy as seen by us in the outside world. This allows the escaping particle to have an equal amount of positive energy. Negative energy? That's weird. Well, it's related to the fact that the nature of space and time reverse roles in the black hole. Recall that in the Penrose diagram of the non-rotating black hole, the singularity at r equals 0 was a horizontal line. That is, it occupies much of space, but at a particular time in your future, you will reach it. It exists over much of space. It's not really a point-like singularity anymore. So this reversal of space and time inside a black hole is sort of qualitatively the way you can think of energy going into a black hole, but with a negative value as seen from the outside world. I'm just trying to give you a heuristic argument about how this might occur. Well, in my class at Berkeley, I illustrate quantum mechanical evaporation of black holes by wearing my black hole suit, having a bucket of celestially themed candy attached to me, orbit gum, eclipse gum, Mars bars, Milky Way bars, starburst candies, and I go flinging those candies out to the students in the room. Years later, they come back and they say, you know, that's one lecture I will never, ever, ever forget. There's other ways of looking at this process of black hole evaporation. One of the favorite ones that physicists have is that black hole evaporation is kind of like quantum tunneling out of a black hole. You know, I'm here, but really, in quantum mechanics says that I'm kind of extended all over the place. And if I hit myself against a wall, there's a very small probability, very, very small, that I will emerge on the other side completely unscathed. Because in a sense, quantum mechanics says that part of me, part of my so-called wave function is out there, not here. And thus there's a chance someone will find me out there. That's called quantum tunneling. And so you can think of these particles tunneling their way out of the event horizon. Now, this reminds me of a joke. What's the difference between an auto mechanic and a quantum mechanic? The quantum mechanic can get the car inside the garage without opening the door. All right. Well, a black hole is observed by its Hawking radiation, and it looks kind of fuzzy. It's a quantum mechanical object, and you can think of photons as escaping through a tunneling process. If the size of the black hole is represented by this little circle here, then it turns out that the flashes of light are fuzzy, comparable in size to the size of the event horizon itself. And the flashes are very faint. For a black hole that's maybe 100,000 solar masses in mass, you will get the emission of only 1 photon per second. So they're really pretty dim until you get to the small ones. Outside the event horizon, photons can escape. The escaping particles and antiparticles can interact with each other, and they also then annihilate and produce more photons. This is then called Hawking radiation. The statistical effect of many such emissions is to produce particles and photons with a thermal distribution of energies, more specifically, a black body distribution. Kind of like coals emit a black body distribution that peaks in the infrared wavelengths. That's what heats our bodies, but you can see a little bit of the red and orange as well, but they peak in the infrared. So you can think of the black hole as, in a sense, having these little jiggly motions, kind of like coals, and emitting the light. The temperature of a black hole is given by the equation Planck's constant h multiplied by the speed of light cubed, c, divided by 16 pi squared, k, Boltzmann's constant, g, Newton's gravity constant, and finally m, the mass of the black hole. This is one of the most beautiful equations in all of physics. It combines general relativity, g, special relativity, the speed of light, quantum mechanics, Planck's constant, and thermodynamics, k, Boltzmann's constant. It is a tour de force. It provides some indication of a deep unification between quantum physics and relativity. Well, notice that the temperature is proportional to 1 over the mass of the hole. As the mass decreases through evaporation, the temperature increases, the evaporation rate increases, and in fact, near the end, the whole thing goes off in a giant explosion. Because the mass is decreasing, the temperature is increasing, the thing is radiating faster and faster. Kablam! That's an explosion. Black holes end their lives under this process through an explosion that emits mostly gamma rays. Could these be the gamma ray bursts that we see? Probably not. Gamma ray bursts that we see don't have the properties that we expect of evaporating black holes. Moreover, if the evaporation rate is proportional to the inverse of the mass, you might say no black holes should be exploding. After all, the stellar mass black holes are pretty massive. The supermassive black holes are really massive. They are gathering material from their surroundings faster than the rate at which they evaporate. However, Hawking has suggested that mini black holes, generally less than 1/1000th of the Earth's mass, might have been created shortly after the Big Bang. And, if there were large fluctuations in the density of matter shortly after the birth of the universe, some of them could have collapsed and formed these little structures. And those might be evaporating. Now, not all models of the early universe come to this conclusion. So the presence or absence of black hole evaporation can help us eliminate incorrect theories. These mini black holes have a high evaporation rate. The ones that were less massive to begin with than the mass of a big mountain, like Mount Everest, would have already evaporated. The other ones, the slightly more massive ones, might be exploding right now. People are looking for them. They haven't found them yet. Maybe someday we will find them. But if we're not finding them because, in fact, black holes don't evaporate, well, then that can tell us something about the grand quantum theory of gravity. Or if we're not finding them because they're simply not there, that rules out some of the proposed models for the early universe. Well, Hawking probably deserves a Nobel Prize for his research. Black hole evaporation is recognized to be a generic feature of just about all attempts to unite quantum mechanics and general relativity into a theory of everything. However, as even Hawking concedes, he is unlikely to get a Nobel Prize until evaporating black holes are actually found. As I'll discuss in Lecture 12, maybe evaporating mini black holes will be produced by the Large Hadron Collider. Ironically, though black hole evaporation is a step on the way to a quantum theory of gravity, it also raised a new mystery that challenged the very foundations of quantum physics. What happens to all the information that went into a black hole after it has evaporated away? We'll discuss that in the next lecture.